All right, number 7. So here we have oppositely charged parallel plates. The distance of separation, distance of separation between the plates is 5.33 millimeters, which you want to put that in meters. When you plug that into an equation, you want that to be meters. We're told that the potential difference, now look, another name for potential difference is voltage. Sometimes problems will say potential difference. Other times they'll use the word voltage. Potential difference and voltage are the same thing. So the potential difference is 600 volts. So here's what that means. The easiest way to do that, the easiest way to do it is go positive plate is 600 volts, negative plate is 0. But just so you're aware, that would be identical to 1,000 volts and 400, or 0 volts and negative 600. As long as the positive plate is at higher volts than the negative plate, you have it set up correctly. But the thing that you're going to care about is the difference between 2 points, okay? So we're given the difference between the plates, 600 volts. So we'll just say 600 and 0. That's the easiest. First question, what is the magnitude of this electric field between the plates? We're looking for the electric field. So there's an equation that can only be used when you're in this situation of having oppositely charged parallel plates, which has a constant electric field. If the electric field is constant, then you can use this equation. Potential difference, or voltage, is equal to the electric field between the plates multiplied by the distance between the 2 points that you're focusing on. And technically this equation says negative, but as long as you know the positive plate is at higher volts, then you don't really need the negative. All right, so real easy. We just go what are we solving for? E. The electric field is going to be the voltage divided by the distance. So that's 600 volts across the plates. And then the distance between the plates is 0.00533 meters, which gives us an electric field of 112,570 volts per meter. Now look, just so you're aware, notice the unit here, volt per meter. That is electric field, but it's also, you could also express the electric field as Newton per Coulomb. These are identical. A volt per meter is the same as a Newton per Coulomb. The units are identical. Okay? It's just, here's the thing. This way is chapter 16, which is energy. This way is chapter 15, which was forces. But they're the same. Okay, part B. What is the magnitude of the force on an electron between the plates? So you stick an electron in here. Now, which way would the force be? Given this diagram, if you stuck an electron in there, would the force be with the electric field, or would the force be against the electric field? It's going to be against, because that's how, an electron would be attracted to the positive plate and repelled by the negative plate. So the way we solve this goes back to last chapter. There's an equation, force of an electric field, not mg, QE. Force of electric field is QE. Okay, so the problem assumes that we know the charge of an electron, which we do. 1.6 times 10 to the negative 19 coulombs, and then we'll use the electric field this way with Newton per Coulomb, 112,570 Newton per Coulomb. Coulombs cancel, and we get force of the electric field equal to 1.8 times 10 to the negative 14 newtons. All right, so A and B were the easier parts. Part C requires a little more thinking. Okay, so part C, how much work must be done on the electron to move it to the negative plate if it's initially positioned 2.9 millimeters from the positive plate? Okay, so let's clean this all up. All right, so we're sticking an electron. In fact, I'm going to erase one of these arrows here. So we're sticking an electron between the plates, and they give us the distance from the positive plate, as if this isn't tricky enough. So this distance here is 2.9. Is that the distance we want? No. The distance that we want is this other distance, which you can just get from subtraction. You go 5.33 minus the 2.9, 2.43 millimeters. That's going to be our distance right there, 2.43 millimeters. Now, the question is, how much work must be done on the electron to move it to the negative plate? So check this out. Does this electron want to go that way? It does not. The electron, if you just stuck it in there and released it, the electron wants to go this way. Okay? So look, I found the best way to explain this. It's going to take me a moment, but I think it's worth it. If you think about the gravitational field, so check this out. So I'm going to stick a little building in here. So here's a situation very, very similar. In fact, so I'll put the building there, and then I want to add this equation. So this goes back to chapter 5 right here. So here's a situation. Imagine taking an object. So let's say it's like just a rock. Okay, so I'm going to get rid of this tree. So we're going to stick a rock at the bottom of this building. If you took this rock, or whatever it is, and lifted it to the top of the building, could you find out how much work was done? I mean, if you had all the data, the mass of the object and how high the building is and gravity. The way that you would find the work done here is the same as finding the work done here. It's pretty much the same thing. The only difference is this is a gravitational field, this is an electric field, but the situations are pretty much identical. Does that make sense? So how would you find the work done to lift this mass to a height h? So the building is h, we got that mass m. Oh, and we're assuming that this is happening at a constant velocity. In other words, we're not going to take this mass and have it go faster, 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 faster. It's just we're going to lift it at a nice constant rate. So how would we go about finding the work done? Well, look, do we have a force other than gravity or spring acting here? So if you're lifting the mass up the side of the building, there has to be some force lifting the object. Okay? So we have the force lifting it is up, and then mg is down. If this mass is being lifted at a constant velocity, what has to be true about these two forces acting on the mass? They're equal. So in other words, our lifting force here is equal to mg. Does that make sense? The force lifting the object, if it's being lifted at a constant velocity, then this force is equal to mg. Okay? Okay, so we're basically looking for this work right here. The work done by the force lifting the object. All right, so put the 0 point right here. Stick the 0 point here. Does the object start with potential or gravity? No. Any spring energy? No. Kinetic initial and kinetic final, if it's moving at a constant velocity, these cancel because they're the same, right? And then any spring energy at the top? No. So basically what we find is this. The work done is equal to the potential energy of gravity gained, right? And look, I'll show you another way. What's the basic work equation? Force times displacement. Well, what is the force lifting the object? The force lifting the object has to be equal to mg, right? So you go, okay, the work F is equal to mg, and then what's the delta x? the H, which is mgh, which is this. Okay, now let's look at the electric field here. I don't know if that's how, to me, that's, when I was first learning this, that's what I did. I related it to gravity. It's pretty much the same thing. Okay, so let's solve it with the electric field. Okay, so we have the electron in here. So put this back. So here's the electron. We figured out the distance it's moving is 2.43 millimeters. Okay, so what are the forces on the electron? We have the force of the electric field to the left, and then we have the force moving it to the right. If the electron moves at a constant velocity, what must be true about those two forces? They cancel. They're equal to each other, right? Those two forces are equal to each other if the electron moves with a constant velocity. Okay? So here's what I would do. You can go work equals force times displacement. Okay? So what is this force? The force moving the electron must be equal to the force of the electric field. Like that. So the force of the electric field, we already know what it is. It's 112,570. We solve for that in part B. And then our displacement is 0.00243 meters. Okay? So this comes out as 4.4 times 10 to the negative 17 joules. That's the work done. But I want to show you one other thing, just so you totally are like the master of this. Could you solve for the work using energy? Yeah. Let's stick that up here. So another way that you could have done this, is you could have been like, all right, potential energy initial plus kinetic initial plus the work moving the electron equals potential final plus kinetic final. If the electron moves with a constant velocity, kinetic initial and kinetic final will be the same. So we can cross those out, okay? Set your 0 point here, right? Say, all right, this is where potential energy is 0, right? And then as the electron goes to the right, it gains potential. So potential initial goes to 0. So the work done is going to equal the potential energy final. Well, okay, so how do you do that? Well, voltage is change of potential energy per charge. So change of potential energy is going to be the voltage times the charge. So take this, plug that in up there. So this is going to be delta V times charge. And then between parallel plates, there's another equation here. Delta V equals what? E times delta X, right? That's the parallel plate equation. Plug that in up there. So now watch. You get Q and then E times X. E delta X. Check it out, dude. I don't know if you see it yet, but look. Does the electric field care about mass? No, it cares about charge. So look, if you were to do this in a gravitational field, the Q would become what? M. The E would become G, and then the delta X would be your H. Bam! You know, so look, this is potential energy in a gravitational field. This is potential energy in an electric field. Did that break your brain? So probably you like the first solution. The first solution might be better. You know, work equals force times distance. Anyway.